show that the subset of R2 given by the set x1, x2, which is in R2, such that the first component x1 is strictly greater than the second component x2 is open. Okay, so they're asking us to show that this set, which we'll call S, so just for short, let S equal this set x1, x2, which is in R2, and R2 is just the coordinate plane. We can think of R2 as just the coordinate plane. And it's especially helpful to think of R2 as the coordinate plane in this particular problem, such that x1 is strictly greater than x2. And we want to show that S is open. Okay, so there are multiple creative ways that you can show that a set is open. But we chose a specific route in this problem, and it might not be the most elegant route, or it might not be the simplest route, but it's a route that certainly works to show that S is open, where we just go straight from the definition of an open set. And again, there might be a more elegant way going a different route. And again, I'll remind you that this is not by any means the only way to show that S, or any set, is open, but this is the way that we just chose, or that I just chose. So an open set is a subset S of a metric space E. So it is defined to be open. That subset S is defined to be open if for any point A in S, and I'll remind you, a subset S of a metric space E. So it's defined to be open if for any point in that set S there exists an open ball with center A that is entirely contained in S. Now, I encourage you not to think of things in real analysis as entirely geometric. That is to say that it's sometimes limiting in our coming up with ideas for proofs and how to prove something if we just think of it in geometric terms. It's sometimes we might want to abandon our geometric notion of things to come up with more creative paths towards a solution. But I think for explaining purposes, I'm gonna illustrate this fact in a geometric way. So let's say that this is our set A, and let's say, so what this kind of means is if I were to take any point in A, so any of these points, I'll always be able to find an open ball with center at any of these points that is entirely contained in A. So no matter what point I choose, let me say that in a different way. No matter what point I choose, I'll always be able to find an open ball that is entirely contained in A. That is to say that there are no points in that open ball that aren't in A. Or another way of saying that is every point that I could possibly choose in that open ball, every point that is in that open ball will always be in A. So, and again, even another way to say that is that open ball is a subset of A. Okay, so in this particular case, I want to show that S is open, and to do that, I'm just going to go straight from the definition. We're going to show that any point in S contains an open ball that is entirely contained in S. So we show, given any point P, which I'll say is equal to P1, P2, any point P in S, we show that given any point P in S, there exists, this is the shorthand for there exists an open ball with center P that is entirely contained in S. Now, how do we do this? How do we show that there exists an open ball with center P that is entirely contained in S? Well, if I say, given any point, so let's take any point P. Let me change colors here. Take any point P in S. Take any point P in S. If I can show that there exists an open ball with center P that is entirely contained in S, then I'll be done. But you'll notice that for an open ball, let me remind you of the definition of an open ball. An open ball with center P naught and radius r is defined to be the set of points, all points P, such that the distance, however we define this distance metric, or however it's defined for this particular set that we're dealing with, or for this particular metric space that we're dealing with, that we might be dealing with in any particular problem. In this problem, we're dealing with R2, which has various metrics defined on it, and we'll use a particular metric. We'll use one of those metrics for this particular problem, but we could be dealing with any particular metric space with any particular metric defined on that metric space. So the open ball is all points P such that the distance between P naught and P is strictly less than the radius r. So you notice in this problem, if we take any point P in S, then there exists. Then we want to show that there exists an open ball with center P and radius r, but we don't have our radius r. We want to show that there exists an open ball with center P and some radius r. But we don't have our radius r. I'm going to emphasize that again. We don't have our radius r. So this problem that we're dealing with reduces down to finding a radius such that any point in our open ball, any point in that open ball will always be in S. And there won't be any points in that open ball that aren't in S. So we need to find a valid radius. This problem comes down to finding a valid radius. And let me illustrate how we might do that. So, remember, R2 is the coordinate plane. It's often helpful in this particular problem to kind of draw out what we're dealing with. Remember, we're dealing with the first component is strictly greater than the second component. All points such that the first component is strictly greater than the second component. So, if the first component, x1, x2, so the first component, x1, is strictly greater than x2, it's often helpful to think of this in terms of just x and y. This is just x, and this is just y. So in this particular case, x is strictly greater than y. And remember, with things like this, all points such that x is strictly greater than y, if we were to draw the point y, the line y is equal to x, y is equal to x. And if we were to take any arbitrary point such that x is strictly greater than y, all of those points lie beneath that line. All of those points, let me switch colors here. All of those points lie beneath that line. So if this is the line y is equal to x, all of the points such that y is strictly less than x are all the points down here. All of the points down here beneath that line. You can think of it beneath that line. So, to find our radius r, if we were to choose any arbitrary point, beneath that line, if we were able to find a distance from that point to that line, and we were to choose a radius for our open ball that is that distance or less, then of course if we had an open ball with center at that point, if we had an open ball centered at that point, and our distance is the distance from that point to the line y is equal to x, or that distance is the distance from that point to the line y equals x, or something less than that distance, then any point in that open ball is of course below the line y is equal to x. So, an excellent candidate for our radius for our open ball that we want to find for each particular point, and that radius is going to be, and you'll see later, is going to be unique for each particular point. It's going to be unique for each particular point, is the distance from that point to the line y is equal to x. It turns out that distance from any point, I'll call x1, x2, from any point x1, x2 to the line y is equal to x, that distance turns out to be x1 minus x2 all over the square root of 2. So I claim that radius, or anything smaller than that radius, for each point x1, x2, if I have an open ball centered at x1, if I have an open ball centered at x1, x2, with radius x1 minus x2 all over the square root of 2, or a radius smaller than this, then I claim that open ball is entirely contained in S. And since x1 comma x2 is any arbitrary point in our set S that we're trying to show is open, and since this x1 minus x2 over the square root of 2 is only dependent on that center point, it's not dependent on any other value, then if I'm able to show that that open ball is with center x1 comma x2 and radius x1 minus x2 over the square root of 2, is that if I'm able to show that that open ball is contained in S, then I've shown that for any point x1 comma x2, because x1 comma x2 is just any general point in S. This applies for any point. This radius and this center point applies for any point in S. So let's do that. Our goal now is to show that the open ball with center x1 comma x2 and radius x1 minus x2 over square root of 2 or smaller. I could even choose a radius that's smaller, and I'm actually going to do that, and you'll see that in a second here. Our goal is to show that that open ball is entirely contained in S. So let's do that. So to do that, I'm going to clear the board first. So let me clear the board here. So, our goal, show that the open ball with center x1 comma x2, and that x1 comma x2, that point is in S, with center x1 comma x2 and radius x1 minus x2 over the square root of 2 or smaller radius is entirely contained. That is to say that if I were to choose any point in this open ball, then that point must be that point is in S. If I'm able to show that if I were to choose any point in that open ball, and show that that point must be in S, then I've shown that this open ball with center x1 comma x2 and radius x1 minus x2 over the square root of 2 is entirely contained in S. So let's do that. But before I do that, I'm going to remind, we're going to use four facts that will come to be useful. 4 facts. The first fact, and you've seen this in multiple videos in the past, that if A is strictly less than B, if A is strictly greater than B, and C is greater than or equal to D, then that implies that A plus C is strictly greater than B plus D. We've seen that in multiple videos, and I've proven it in a separate video that I've linked in the description in the top right corner here. So that's one. Our second fact that might seem obvious, but it's worth noting because I'm going to be using it a lot. So the absolute value of A is greater than or equal to A for any real number A. And moreover, the absolute value of A minus B, which is equal to the absolute value of B minus A. This is a fact I've also talked about in previous videos. That is strictly greater than or equal to, it's just greater than or equal to A minus B. Now, before I talk about facts 3 and 4, I'll remind you that we can use the following distance metric defined on R2. The usual distance metric defined on R2 is the following. The distance between any 2 points x and y, and I'm doing them as vectors because their x is equal to the 2 tuple x1 comma x2, and y is equal to the 2 tuple y1 comma y2. That the usual distance metric defined in R2, I'll say usual in quotes, so the usual distance metric is the following. It's just the distance formula, if you remember from way back. So this is x1 minus x2 squared plus y1. Oh, excuse me, sorry. This is x1 minus y1 squared plus x2 minus y2 squared, all square rooted. So that's the usual distance metric defined on R2. And so this leads me to my third fact that will come in handy here, that the absolute value of x minus y, x1 minus y1, is less than or equal to the square root of x1 minus y1 squared plus x2 minus y2 squared. Cool. So that's cool. And the fourth fact, and you'll see what I mean by this in a second. The fourth fact, and really it's not really a fact, it's more of a technique. So this is really a technique here. Is the technique of cleverly adding 0 to get what we want. And you'll see what I mean by that in a second. To get what we want. Okay, so let me remind you of our goal here. Our goal here is to show that if I have a point x1, x2, then my goal here is to show that any point in the open ball centered at x1, x2. And let me remind you what that open ball looks like. So any point in this open ball, all points p1, p2, such that the distance between x1, x2 to the point p1, p2, the distance between x1, x2 and p1, p2 is less than that radius that we talked about way upstairs and last time that we derived is less than x1 minus x2 over square root of 2. Our goal is to show that any point in this open ball centered at x1, x2, which is in S, our goal is to show that p1, p2, goal, show that p1, p2 is in S. But remember, if we're able to show that p1 is strictly greater than p2, if we're able to show this, then we've immediately shown that p1, p2 is in S. So remember, if p1, is greater than p2, then that implies that p1, p2 is in S. Because remember, look at how S is defined. S is defined. This is our set S right here. Remember, we defined that way at the beginning. So remember, if the set S is defined as all points in R2, such that the first component is strictly greater than the second component of the two tuple. And so if we're able to show that the first component of P is strictly greater than the second component of P, where P is any point in this open ball, then we've shown that P1, P2 is in S. And that is to say, and if we've shown that any point in this open ball is in S, then we've shown that this open ball is entirely contained in S. That is to say that we've shown that if we were to choose any point in this open ball, then that point must be in S. So let's do that. So let me do some erasing here. So first of all, remember that I can choose any radius that's of this length or smaller. So I'm going to actually choose a smaller radius. So we want to get rid of that square root of 2 on the bottom because that's a little cumbersome. So since 2 is strictly greater than the square root of 2, then remember, if I have x1 minus x2 over the square root of 2, if I have two fractions with the same numerator and two different denominators, then the fraction with the bigger denominator is going to be smaller. So this fraction right here is going to be strictly greater than x1 minus x2 over 2. So I've found a radius that is smaller than this guy and that is a little bit easier to deal with. So let's now let our radius be x2 over 2. So let our radius equal x1 minus x2 over 2. So now let P, which is equal to P1, P2, be in the open ball all points P such that the distance between X and P is less than our new radius, x1 minus x2, all over 2. Let P be in that open ball. Then we show we show that P1 is strictly greater than P2. Or I should have said A here. This is all points A. These points, this is just any point A such that the distance between X and A, the distance between X and A is less than this radius that we've chosen. So now, if P is in that open ball, then of course it is a point A such that the distance between X and A, it is a point A such that the distance between X and that point that's in that open ball must be less than the radius. So we know for sure that the distance between X and P, which remember we're defining to be the distance metric, this distance metric, which is the square root of x1 minus p1 squared plus x2 minus p2 squared. That distance is going to be less than, strictly less than, the radius, which is in this case x1 minus x2 over 2. And remember our third fact here. We can use this fact right here. We can say that x1 minus p1, the absolute value of x1 minus p1, is going to be less than or equal to this guy right here. And therefore, the absolute value of x1 minus p1 is strictly less than the radius. So this point will come in handy in a little bit here. So, let me move up here so I can have some room here. Let me move up so I can have a lot of room. I'm going to clear some of this out of the way. Okay, so now comes what is in some ways the trickiest part of the argument. So remember, we wish to show that P1 is strictly greater than P2. Or in our case, which is the same as saying that P2 is strictly less than P1. So this is where we're going to use our cleverly adding 0 to get what we want technique. This is going to come in handy. This technique is going to come in handy for us in order for us to show that P2 is strictly less than P1. So we're going to start with P2, and of course P2 is equal to P2 plus, and this is where I'm going to cleverly add 0. I don't mean to boast or anything, but the reason I'm saying that cleverly add 0 is cleverly add 0, that's a term. Cleverly add 0 is a term from Paul Zeit's book, The Art and Craft of Problem Solving. I encourage you to check out that book whenever you get the chance. It's a great book for problem solving and proofwriting. But remember, P2 is equal to P2 plus P1 minus P1. And I'm gonna deliberately add 0 here again. My adding 0 here is deliberate, I assure you. So P2 is equal to P2 plus P1 minus P1 plus x1 minus x2 minus x1 minus x2. Again, P1 minus P1, that's just 0. This is just 0. And then this, x1 minus x2 minus x1 minus x2, that is just 0. And check out what we can do here. We can group specific terms. We can deliberately group specific terms so that we get an x1 minus p1 eventually, an absolute value of x1 minus p1. And also, I forgot to mention that in the same way that the absolute value of x1 minus p1 is less than or equal to the square root of x1 minus p1 squared plus x2 minus p2 squared, we can say a similar statement for x2 minus p2, the absolute value of x2 minus p2, in the same way that this is true. We can say that the absolute value of x2 minus p2 is less than or equal to the square root of x1 minus p1 squared plus x2 minus p2 squared. And we can sort of see that this is true. If we were to square both sides, we would get x2 minus p2 squared less than or equal to x1 minus p1 squared plus x2 minus p2 squared. And this fact is certainly true because x1 minus p1 squared, that value is either equal to 0 or greater than 0. And so therefore this x1 minus p2 must be less than or equal to this right-hand side, since this value right here is less than, this value right here is greater than or equal to 0. So we want to group together terms so that we get an x1 minus p1 and an x2 minus p2. And we can do that. Check this out. So if I move over this p2 to be grouped with this x2, this negative x2 to be grouped with this p2, so I get p2 minus x2, And I'll remind you, we're going to use the fact later that the absolute value of x2 minus p2, that's the same as the absolute value of p2 minus x2. That'll come in handy later. And so we're going to group together that term, p2 minus x2, and then we're also going to group together this positive x1, and we're going to group that together with the negative p1. So we're going to have plus x1 minus p1. And then we're going to add all of that. So after grouping those terms together, we get as left over the terms that we didn't group. We're going to have p1 minus x1 minus x2. And check this out. We know the following fact. We know that the absolute value of p2 minus x2, that absolute value is greater than or equal to p2 minus x2. And we also know that the absolute value of x1 minus p1 is greater than or equal to x1 minus p1 without absolute values. And this is directly because of this fact. The absolute value of a is greater than or equal to a for any real number a. And again, that generalizes to this, or that more specifically for our purposes, the difference of two numbers, the absolute value of the difference of two numbers is greater than or equal to the difference of those two numbers without absolute values. So we can say the following fact. That this expression right here, this expression right here is equal to this expression on this second line, and this expression, that expression right there, this expression on the second line, that is less than or equal to the absolute value of p2 minus x2 plus, and let me clear some room here, plus the absolute value of x1 minus p1 plus p1 minus x1 minus x2. And remember, the reason this is true is because the absolute value of p2 minus x2, that's greater than this term right here. And the absolute value of x1 minus p1, that's greater than this term right here. Let me color code this. So this term right here is greater than or equal to, I'm writing this greater than or equal to vertically. And then this term right here, this is greater than or equal to the term above. So the absolute value of x1 minus p1 is greater than or equal to x1 minus p1 without absolute values, and the absolute value of p2 minus x2 is greater than or equal to p2 minus x2 without absolute values. So if I were to sub both of these absolute value, the difference, both of these absolute value of these differences into this expression right here, if I were to sub those into this expression right here, I would get a new expression that is greater than or equal to this second line right here, the expression that's on the second line. And that's directly because of applying this fact. I won't go into the details of how I applied this fact, but these two are the larger terms. And if I were to sub in a larger term for this term and a larger term for this term, I would get a new expression, keeping the rest of the expression the same, that is greater than our original expression. But again, if you want to see a more rigorous argument, you can apply this first fact right here. So check this out. I get this new expression right here. And let me clear some room here so that I can finally finish out this argument. So remember what we have down here. We have that the absolute value of x1 minus p1 is less than or equal to the distance between x and p, which is strictly less than the radius of our open ball. So therefore, the absolute value of x1 minus p1, the absolute value of x1 minus p1, this guy right here, that's going to be strictly less than our radius. And also this guy, p2 minus x2, I'm going to write out my equal sign vertically here. Let me change colors. This guy right here is less than or equal to our radius. And this guy is equal to, remember, x2 minus p2. Remember, the absolute value of a minus b is the same as the absolute value of b minus a. The absolute value of a minus b is the same as b minus the absolute value of b minus a. And this is equal to the absolute value of x. So absolute value of p2 minus x2 is equal to the absolute value of x2 minus p2. And that is less than our radius. That is less than our radius. And by the same reasoning that I used before, where if I were to keep this whole expression the same, except that I would sub in for this term a larger term, and I would sub in for this term a larger term, and keep the rest the rest of the expression the same, then I get a new expression that's larger than our original expression. That is to say, since I'm subbing in a term that's strictly greater than this term, and I'm subbing in another term for this term that's strictly greater than this term, and keeping the rest of the expression the same, I get a new expression that's strictly greater than our original expression. That is to say, I'm subbing in for this term the radius, because the radius is strictly greater than this term, which is also equal to this term, which the radius is strictly greater than. And that radius, remember, is x1 minus x2 over 2. And same thing for this absolute value of x1 minus p1. I'm subbing in the radius, which is strictly greater than this term. So I also have plus x1 minus x2 over 2. And I keep the rest of the expression the same, plus p1 minus x1 minus x2. And check out what I have here. Grouping these two terms together, they have the same denominator, so I can add them together. I get x, this is equal to x1 minus x2. x1 minus x2 over 2 plus x1 minus x2 over 2 is equal to x1 minus x2. And this, I'm adding to p1 minus x1 minus x2. And look at this. These guys cancel. These guys cancel. These guys cancel. And check this out. This is equal to P1, and look what I've just shown by these series of inequalities. That P2, boom, 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 is strictly less than P1, aka P1 is strictly greater than P2. So therefore, I've shown what I've wanted to show. I've shown that this point P, which is any point in our open ball of radius x1 minus x2 over 2, with center any point x in our set that we now know is open, S, in our set S, I've shown, well, we don't know it's open until the very end of this argument, but I've shown that this point P is a point in S because P1, the first component, is strictly greater than P2, and therefore, I've shown that this open ball must be contained in S, and I'm finished.